In the standard SHDC CPU architecture, rotational dynamics are driven by a single scalar value, represented by energy. This single floating point number dictates a locked, localized rotation strictly around the inverse axis, creating a holographic wrap. The nodes are colored by their orientation. Because they only rotate around the y-axis, their top faces green, always point up. The memory cost is 1 for byte float per node. With 64 nodes, that equals 256 bytes per packet. To increase topological complexity, we extend the packet so that every single node maintains its own independent, full 3D rotational state via a unique quaternion. The system shifts from a scalar-weighted grid to a highly chaotic tensor field. Notice how the nodes in the viewport now rotate freely on all three axes. X equals red, Y equals green, Z equals blue faces are visible everywhere. Memory cost is 4, 16 byte floats per node, where 64 nodes equals 1024 bytes, or 1 kilobyte. Across a million packets, this requires 1 gigabyte of VRAM solely for rotation. To fix the memory bottleneck, we exploit a geometric property of rotational quaternions. They are always unit vectors bound to the surface of a 3-sphere. This means their magnitude is exactly 1. Because of this strict boundary, if we know any 3 components, we can always calculate the absolute value of the fourth, because the nodes are computationally bound to the exact mathematical surface of the unit manifold. An uncompressed quaternion requires 4 standard floating point numbers, which is 128 bits. To find the largest, we evaluate the absolute values of W, X, Y, and Z. Then, let's assume W is the largest component. Then, we drop and index. To do this, we drop W entirely to prevent precision loss during mathematical reconstruction. To remember which component we dropped, we store a 2-bit index, where 0, 0 equals X, 0, 1 equals Y, 1, 0 equals Z, 1, 1 equals W. We are left with 3 floating point components, X, Y, Z, and a 2-bit index. The remaining 3 components are mathematically mapped from their floating point range into 10-bit integers. We then pack them together into a single standard 32-bit and signed integer with bitwise assembly. Full 3D rotational states are compressed from 128 bits down to 32 bits, reducing our memory footprint to 256 bytes per packet without losing visual precision. Even with memory optimized, calculating 64 independent physics-based quaternion integrations on the CPU per frame is expensive. We bypass this using the geometric symmetry of the lattice. Instead of calculating 64 rotations, we calculate rotations for only 1/8 of the lattice, the master octant, highlighted in bright white in the viewport. The other 7 octants, dimmed, simply copy the master octant and apply a quaternion conjugate operation to mirror the rotational physics symmetrically across the coordinate axes. The final optimization replaces continuous physics integration entirely. Since the packet operates on a strict sequence, quaternions don't need free 3D rotation. They only need to interpolate between predefined target states mapping to the 7-Strassen matrix multiplication steps, M1 to M7. We replace complex integration with a fast spherical linear interpolation called SLIRP, which is tied directly to the global sequence cycle T. The chaotic tensor field has snapped into strict, synchronous formations, interpolating smoothly between predefined geometric locks. The symmetry inheritance from the master octant 1/8 of the nodes doesn't just save CPU cycles, it establishes a fractal unfolding structure. By mapping the spatial interaction between the master quaternions and their symmetrically mirrored conjugates, we generate a 3D interference pattern known as a holographic scalar field. The master octant, cyan, operates freely, while the rest of the lattice reflects those rotations as continuous, pulsating scalar interference bands, shown as dark magenta, unfolding fractally across the packet volume. Because the holographic scalar field is perfectly symmetrical, it supports non-dispersive pressure waves called solitons. More importantly, because the entire 64-node wave is a fractal reflection of the master octant, we can extract the global directionality, a 3D vector, of any moving wave by observing only the 8 nodes in the master octant. Notice the viewport, a high-energy soliton wave, pink/yellow, sweeps back and forth through the lattice. The directional vector arrow is mathematically tethered strictly to the center of the master octant, yet it flawlessly tracks the global trajectory of the entire system.